Hi, welcome to Math 331 Problem Solving Lecture 11. What I want to do today is I want to talk about looking at new material coming from things that you know very well, and getting you in the habit of asking questions. So I want to start with something that if you have not seen, you need to fake that you've seen it. You will have to do this occasionally in life, and you just look at it, look it up when you get home. All right? Everybody, I'm sure, is familiar with the Pythagorean theorem, so I'm not even going to bother stating what that is. All right. So often in mathematics, we have multiple proofs. If you're listening carefully, we talk about a proof of the following, not the proof of the following. Very rarely does something make it to the proof. There's a few things where this is the right way to look at things. But for a lot of problems, there are multiple perspectives, and different ones give you different insights. We saw this, for instance, with the arithmetic mean, geometric mean inequality, that by looking at it different ways, we got different pieces of information. A lot of times, you prove things by algebraic brute force. Have you heard of Morley's theorem? If you take any triangle, if you trisect each of the angles, and for each side look at the two bisectors or two trisectors that are closest to it, that will give you 3 points. What kind of triangle do you think those 3 points always determine? There's only 2 possible guesses, and by symmetry there's only 1. What kind of triangle? It's going to be a triangle with a name.
A right triangle.
That's one of the possible guesses. It's the wrong one.
Equilateral.
It's an equilateral triangle, because if it's a right triangle, then one angle would be privileged over the others. So no matter what triangle you start with, if you trisect and connect those points, you always get an equilateral triangle. So my first year at Princeton, I was walking to the office with a couple of my other grad students, and we were talking about this, and I remarked, oh yeah, it's really trivial to prove this. And my friend goes, really? Oh yeah. Just write down the equations of the points and calculate the equations of the intersections. And so he bet me not that I couldn't, but that I wouldn't have the patience to finish the calculation before we graduated. So the deal was, if I do it, he owes me dinner not to exceed $12.50. This was over about 20 years ago, so that's actually not bad. If I couldn't do it, I owed him ice cream not to exceed $2.50. I actually have the receipts in my office framed. I bought him the ice cream even though I did it for teaching me a lesson. Just because you can solve something with algebra does not mean you should solve something with algebra. So, a year and a half later, I gave him the solution. I was not working on it steadily. It turns out that I found the easiest variables to use was like the tangent of 1/3 of the angles. I ended up getting equations in 2 variables of degree like 48 for the lengths of the squares of the sides between 2 of the points. And then you just showed that those polynomials have the same coefficients, and I was allowed to use Mathematica to expand, and then you're done, and there's the proof. It's entirely unenlightening. Conway, and we will meet John Conway many times in this course, has a better proof where you start off with an equilateral triangle, and you reverse engineer to get the triangle you want. And that's a proof where you really see what's going on. So a lot of what I want to do today, it's not going to be giving you a huge amount of material. It's really emphasizing how to look at problems, how to think about problems. We very rarely have the opportunity in math classes to do this. There's always this pressure, this rush to get through material that you'll never use in the rest of your life. So rather than going into that pressure today, rather than doing all the algebra, let's actually spend the time and do it slowly. All right. So we're going to check special cases and use special cases to build up intuition. That does not mean we've proven things, but at least we get on the right track. All right, so the Pythagorean theorem, as everybody knows, a squared plus b squared equals c squared. The only real debate is which is a and which is b, and do you draw the right angle here or do you draw the right angle there? If I were to draw this many times, I'm sure I would flip back and forth as to which way I do it. Does not really matter. Okay, how many of you know a proof of the Pythagorean formula? Okay, so.
You could do law of cosines proof and then just...
No, you cannot do a law of cosines proof. How do you prove law of cosines?
I did it. It was in the homework. So.
Right, but I'm saying, what do you need to prove the law of cosines?
You need the
Pythagorean. So you've got to be very careful not to use. So if people are interested later in the term, I can talk about a proof of mine using the Riemann zeta function and the irrationality of pi squared to prove not only that there are infinitely many primes, but to get a sense of how many there are. So you might be familiar with Euclid's proof, multiply all the primes, if there's only finitely many, add 1. Either it's a new prime or divisible by a prime not on the list. That actually gets you a growth rate of primes of like, it's at least log x primes up to x. The growth rate sucks, okay? The real answer is about x over log x. Well, it turns out that the sum of 1 over n squared is the same as the product over primes of 1 minus 1 over p squared inverse, and that's pi squared over 6. And because pi squared is irrational, you can use this to prove there are infinitely many primes. We can talk about this later. And then by knowing how irrational pi squared is, you can actually get estimates as to how many primes there are up to x. And so I was able to use this. I couldn't quite get, in my initial attempt, Euclid's result of log x. I got there at least log x primes up to x. And I didn't realize at first, but the result about how irrational pi squared is used the prime number theorem, that there are x over log x primes up to x. So by assuming that there are x over log x primes up to x and doing a lot of work, I'm able to show that there are at least log x primes up to x. It was probably the worst result I had proven up until that point in my career. So then with some students, including some Williams students in the past few years, we actually opened up the proof of the irrationality of pi squared and said, well, what if we don't assume the prime number theorem? What if we assume weak results and do things recursively and feed things in? And then we're actually able to infinitely often get almost x over log x. So in the end, the result was actually a nice result. The initial result was very bad. So you've got to be careful, and so thank you for highlighting this, that when you prove things, you do not implicitly assume what you're trying to prove. You do not use any consequences of it. One of my least favorite weeks of teaching is the beginning of complex analysis, because I always forget, what have we assumed at this point? Once you finish the course, then you always integrate freely and you change contours. But at the beginning, well, we've only done it for triangles, and then we've done it for rectangles, and you've got to be careful as to exactly what you can use. So does anybody know a proof of Pythagoras? All right, so we will at least give some classic proofs of Pythagoras. This is one of the famous ones going all the way back to Euclid. If it's in color, it looks a little bit better, and gives you maybe some idea of what goes with what. And then the hope is that this is enough of a clue to figure out what's going on. I've never really bothered. I'm sure this is right. I found it through a Google search. So got lots of colors, and you seem to have one of each color, so that's a good start. But I have absolutely no desire to go through and show why each of these matches up with the others. This is the first proof I really remember. My physics professor, who was a great mentor to me at Yale, showed me this one. So let's take 4 right triangles, and we'll do A followed by B, A followed by B. And what's nice is, if this angle is theta, this is 90 minus theta, this is 90 minus theta, so this is 90 degrees. So this is a square inside. So we do one of our standard tricks. We calculate something 2 different ways. The area of the big square is A plus B squared. It's also C squared plus 4 times the area of a triangle. Well, do we know the area of a triangle? No. But we know the area of a right triangle, because a right triangle is half a rectangle. And we will assume we know that the area of a rectangle is just x times y, length times width. So it's, what am I assuming? Now that we know that the area of a rectangle is length times width, we can get the area of a right triangle is 1/2 length times width. And so you'll notice the 2 ABs will cancel, and you're left with a squared plus b squared is c squared. If you want to arrange it slightly differently, here's another way of doing it, and you can see the a squared, the b squared, and then the 4 triangles fitting together nicely. All right. One of the most famous alums of Williams, ascended to the presidency of the U.S. How did he die?
Shot on his way back from
Yes, I think it was like 25th reunion. So just be careful, okay? I don't want that happening again. No deaths coming to our reunions. We want you to come and spend money in the town and help support the local economy. Donate to... Yes. He was assassinated while coming to his Williams reunion. Yes. Yes. So he is credited with a proof of the Pythagorean theorem, the only U.S. president credited with a proof of the Pythagorean theorem. I will not remark, since this is being recorded, whether his brilliant trapezoidal proof is significantly different than these other ones. All right, so there's lots of different proofs. One of the big questions, of course, is how the hell do you find some of these combinations? You know, if you go back to this monstrosity, where the heck? Okay. At the end of the day, though, do you have any idea why it's true? It's a result. It's a fact. That's good. You know, we'd at least like to have the fact to use. But more than that, I'd like to understand why it's true. And then maybe I can prove some other stuff. So what I want to do is I want to introduce you to one of my favorite techniques. It's called dimensional analysis. How many of you have heard of dimensional analysis? Okay. If you have a chemistry accent, you might have heard it as maybe factor labeling a little bit. There's some similarities between this. So what you can often do is you can get an idea of what's going on by thinking of the dimensions. So here, we'll treat this as like a GRE or an SAT. We have 5 candidates for the Pythagorean theorem. Okay? Any of them right? No. But which one of them at least has a chance of being right? So could the first be correct? Why not? Units. This is an area, this is a volume. So this is clearly off. What about the second one? Units work. What do you think? Could this be the Pythagorean theorem?
No, but yes.
Okay. But can you eliminate it? I want you to be able to eliminate it for some reason. What don't you like about this formula?
It's asymmetric.
It's asymmetric. We have a 2b, not 2b, right? We should not have the 2b. Because you really can't tell the difference between a and b in this. What about the next one, a squared minus b squared? Okay, why is that one bad?
Negative area.
Yeah, you could actually have a negative area. Okay, that's clearly bad. What about a squared plus ab plus b squared? Ooh, this is the first one that looks like a legitimate candidate. Everything is dimension 2. It's areas, never negative. It's symmetric. It's wrong, but it's at least a good wrong answer. What about the last one? Do you like the last one? So it's also symmetric, never negative. If you think about it, there is an issue with the last one, then you can eliminate it.
If you
I mean, if you plug in 1 everywhere.
Oh, so this is now trying to go into a special case. So what's going to be the contradiction if you try to put a equals b equals 1?
You're going to have an absurd area.
You can have an absurd area. You can have an absurd value for c. When you have a triangle, the sum of any two sides must be greater than the third. If you look at a plus b squared, that's a squared plus 2ab plus b squared. This has an extra 108ab. This is going to be far more than a plus b squared. So there's no way it can work. Yes?
Can you explain the symmetry disqualification thing a little bit more?
Sure. I mean, when you look at this, there's really no way to tell the difference between the role A and B are playing. They're both sides of a right triangle. So you expect your answer to be symmetric in A and B.
Right, because you could just swap.
Because you can just swap what you're calling A and B.
Yes.
And your formula should not be able to detect the difference.
Right.
Now maybe there is something with minimum side and maximum side, but not really thinking that way.
Yeah.
Okay. So the only one that passes on the test is this one, which will of course later fail, and that violates A plus B being greater than C. All right. So here's the dimensional analysis proof of the Pythagorean theorem. This is my favorite proof. This is the one my physics professor showed me. Do you agree that area is a function of the hypotenuse and the angle? That all you need is those two values and everything else is determined. Without going into what sine and cosine are, A would be C sine x, and B would be C cosine x, and the area would just be 1/2 C squared sine x cosine x. Did you have a question?
It's just assuming it's a right triangle.
Yes. So we are doing a right triangle. So everybody agrees that the area is a function of the hypotenuse and the angle x. if I use these things called sines and cosines, I can even write down explicitly what it is. Do you agree that it depends on the square of the hypotenuse?
Yeah.
If I triple C, I'm going to triple A and B, so the area is going to go up by a factor of 9. So I can write the area as a function of the angle times C squared. I don't know what this function is. Well, technically I know it's 1/2 sine x cosine x, or 1/4 sine 2x, but I don't really know my sines and my cosines. But I know it depends on C squared. Does anybody remember what the one thing you have to do in all good geometry proofs?
Draw some useless lines.
No! It's actually pronounced auxiliary. It all comes down to drawing an auxiliary line. What kind of line would you like to draw here? What would you love that line to give you?
A rectangle.
Not a rectangle. We would like to draw a line, and what would we like that line to yield for us?
Like a new right triangle?
Yeah, new right triangles. So where do you want to draw the line from?
Like at the intersection of A and C.
The intersection of A and C?
Bring it down to that.
Well, there's no way to bring this down
Oh.
A and B.
A and B
Yeah, A and B.
and go up to here, right?
That would have been more obvious choice.
And so, in a burst of creative insight, we will name the new triangles 1 and 2. Isn't it nice? And of course, 1 should be closer to A and 2 should be closer to B. I mean, that's just a given. What do we know about these triangles? We know they're right. What else do we know?
They're similar to each other, it's the big one.
They're similar to each other because they all have an angle x and they're all similar. So they're all similar. What do you know about the area of little triangle 1?
Depends on A.
Depends on A. How does it depend on A?
In the same way.
Yeah, in the same way. So we get f of x a squared plus f of x b squared is f of x c squared. What can you do now? All right, so playing that little clip of Cam did not help you. Assuming, yes, thank you. Assuming that f of x is not 0, right? You really don't want to wear, a scarlet E for economics or a scarlet P for physics on your forehead, right? Is f of x 0? No. If f of x was 0, the triangle would have 0 area. Okay, we know as long as a and b are not 0, the area is not 0. So we know f of x is not 0, so we can divide by it, and now we get a squared plus b squared is c squared. So this is the dimensional analysis proof of Pythagoras. All right, to give you another example, how many of you remember pendulum bobs from like high school physics classes and trying to calculate the period? Does anybody remember the equation for the period of a bob? So most physics labs and chemistry labs are often done before you get to the lab. Some schools have professors who deliberately miscalibrate instruments so that they can tell if you've actually done the experiment or are just doing theory and putting in small errors. Let's analyze this using dimensions. What do we have? We have the length of the bob in meters. We have the acceleration due to gravity in meters per second squared. We have the mass in kilograms. We have the period in seconds. And we have an angle in radians. And remember, angles are unitless. The period is in seconds. We need to somehow combine these other items to get seconds. Is there any item that cannot come into play? Yeah, the kilograms. There's no way to cancel the mass. The period must be independent of the mass. What does the period have to be a function of? Acceleration, length, and angle. So how does it have to depend on the acceleration and the length? Yes?
It has to depend on the inverse square root
Of,
acceleration
and anything else?
and the square root of
Yes, what I would say is, if you take L divided by G, that's going to be second squared. So it's the square root of L over G. So we know it has to look like something square root of L over G, some function of X. So if you were to quadruple the length, you would double the period. So before you even go into the lab, you have some idea of what to expect. This is the power of dimensional analysis. I remember when I was a senior at Yale, I was taking a complex analysis class, and the professor had an integral we needed to bound, and he wrote the answer on the board, and I raised my hand and said, Professor, this is wrong. The units don't work. I said, I'm sorry? Oh, I'm sorry. I'm in a math class right now because I was a double major. The degree of homogeneity in the parameter A is wrong. Oh, yes, you're right. So you can put this into the context of math. If you have e to the ax, if x is in meters, a should be in 1 over meters. And you can use this to get a sense of what these integrals should be before you actually do the evaluation. It's incredibly powerful. All right. So this is in some sense going to be a little bit of a willing suspension of knowledge. We want to try to guess the Pythagorean formula. Okay? I checked. I am not allowed to bring a keg of beer to class to get you into the right frame for something like this. We have unfortunately perspectives visiting who are almost surely not 21, and it would just create the wrong environment. So we're going to have to try to forget what we know about Pythagoras and just try to think what might be a reasonable guess. Okay? So we want to have some free parameters, and we want to try to figure out what they are by special cases. And so some natural guesses is maybe it's a linear relationship, maybe it's a quadratic relationship, maybe it's a cubic relationship. So let's guess a linear relationship. Let's guess C is alpha A plus beta B for some alpha and beta. Now, of course, this is bullshit, right? But let's try to see if this were Pythagoras. What would A and B, what would alpha and beta have to be? So do you have any thoughts on what we should look at? Yes?
They need to be equal to each other.
So they need to be equal to each other. Good. What else? Do you have any idea what their value should be by looking at some special cases?
I mean, if it's linear, if you have C and then alpha plus beta B, don't you have the issue that, never mind.
Well, you're close. So if they're both equal, what might you need to know about? Yes?
Can't be bigger than A or B.
Remember, A and B are free parameters from the different triangles we look at. So you're close.
It can't be bigger than 1.
They can't be bigger than 1, because they have to be the same. And if either one of them is bigger than 1, so is both, and this violates the triangle inequality. Are there any good triangles to look at? Yes.
45, 45, 90.
Oh, so you know what the hypotenuse is in the 45, 45, 90 triangle? Wonderful. Please, what is it?
Is root 2.
And how do you know this, my friend? So we seem to be going in order down the class. I think you're next for assuming something, right? We do not know that it is root 2. This is why I said it's hard to play this guessing game, because we know so much. We do not know it's root 2, right? How do you prove that it's root 2?
Okay, let's use a 30, 60, 90.
Okay, and what do you know about a 30, 60, 90 triangle?
It's if the bottom is 1, or
Right.
the shorter leg is 1, then the hypotenuse is 2. And I don't know the Pythagorean theorem to prove that.
Okay, so for the 30, 60, 90 triangle, yes, if one of the sides is 2, the bottom is 1.
Yeah.
We don't know what the vertical side is.
Oh yeah, we don't.
You can just draw one equilateral triangle,
Right.
and then bisect it, and
Yeah.
you have 2 right triangles.
But we don't know how long.
But we don't know what the height is. We know the base and we know the hypotenuse, but we don't know the height.
We could use Huron's formula to get the area, and then do base times height.
And out of curiosity, where does Heron's formula? Do you know the song "I Need a Hero"? Anybody know that song? No.
It's the one in Shrek, right?
Yes.
Yeah.
Email me for cultural credit. Yes. They do play that in Shrek.
Why do we know that one side is 1 if the hypotenuse is 2?
Well, because we can at least say that if we have an equilateral triangle, that you bisect the bottom by symmetry.
Right.
So rather than trying to look at a specific nice triangle, look at an extreme case. What might be a good extreme triangle to look at? What kind of property? Yes?
One of the sides is infinitely small.
Yeah! Let's look at a side that's infinitely small, not drawn to scale here. So if this side B is infinitely small, and then approximately what must A be relative to C? They've got to be about the same. And so as A goes to 0 or B goes to 0, we get very thin triangles in both regards. And so the only way it's going to work is if they both equal 1. Do people agree with this? That if we look at the limit as either A or B goes to 0, then C and A have to be converging to the same length, or C and B have to be converging to the same length. So without using a specific known triangle, we can use that to get alpha equals beta equals 1. So then does C equal A plus B make sense? No. So here's a proof. The area of a rectangle is x times y, area of a right triangle is 1/2 xy, and now we'll use your 45, 45, 90 triangle. But we'll use it in a very careful way to deal with areas. So we will now assume that there is such a thing as a 1, 1, 2 right triangle. That's what we would get if alpha equals beta equals 1. We would get the 1, 1, 2 right triangle. Well, we can now calculate the area two different ways. One is it's a 2 by 2 square, which is 4. And the other is we have 4 triangles that are 1 by 1. And so if it's 4 triangles that are 1 by 1, each one of them has an area of 1/2, so the total area is 2, but this way the total area is 4, contradiction. So there cannot be a linear relationship. Okay? It doesn't prove that it's a quadratic relationship, but it just disproves the existence of a linear. Let's go to the quadratic case. So let's say we have alpha A squared plus gamma AB plus beta B squared. What are alpha, beta, and gamma? Can anybody give me any thoughts? What should be true? Yes.
Alpha still equals beta.
Alpha still equals beta. What else about alpha and beta? So they're definitely equal. What else?
Well, based on the last
Yep.
time, like alpha and beta, that logic still holds.
Yeah, that logic still holds by looking at those extreme triangles. Right? So there's incredible value by looking at extreme cases. By looking at the extreme cases, we know alpha and beta have to be 1. Now we're just down to gamma. Gamma better not be more than 2. Because if gamma is more than 2, we're going to violate the law of triangles. So let's look at special cases as before. We know alpha equals beta equals 1. The difficulty is gamma. So let's say we have, again, a 45, 45, 90 triangle. So we have a hypotenuse of size C. Right? Calculate things two different ways. The area is going to be C squared, and it's also going to be 4 times 1/2, 1 times 1. So we get C squared is 2, or we get C equals the square root of 2. Hey, finally! Did we just prove C equals the square root of 2?
In this case.
In this case, that if this relationship holds, then it forces C to be square root of 2. We have not proven that yet. So what will it tell us? Well, if C equals the square root of 2, and C squared is supposed to be this, and we know alpha equals beta equals 1, then we get 2 equals 1 plus gamma, 1 times 1 plus 1, so gamma is 0. So by looking at the 45, 45, 90 triangle, we can see now that the only thing that would be consistent is C squared is A squared plus B squared. Again, not a proof. But now there's only one possible quadratic relationship. Maybe it's really a cubic relationship. Maybe it's a quartic relationship. But if it's going to be quadratic, this is the only one. All right. I know I've done this for all of you, correct? We've done this in this class. So we will put our perspective on the spot. Is the algebra correct? Yes or no?
Yes.
12 over 24 would be? I get a quarter. Do you know why I get a quarter? Well, 16 over 64, you cancel the 6 and you get 1 4. 19 over 95, you cancel the 9 and get 1 4. So we have some incredibly advanced arithmetic here. So just because something works for a couple of cases does not mean it continues to work. Right? This is the issue you have to worry about. Just because we've checked and we've seen the Pythagorean theorem works for the 45, 45, 90 triangle now, does not mean it's always going to work. In fact, we still haven't even proven that it's root 2. We've just said that the only thing that's possible, that's consistent, is root 2. All right. Now we get to the fun part. Have any of you ever studied the Pythagorean formula on the sphere? Why not? So I'm actually being serious now. I know that doesn't happen often. Why haven't you thought about the Pythagorean formula on the sphere? Have you known the Pythagorean theorem at least since high school? Have you known about spheres since high school? Right? Why haven't you connected them?
I don't like geometry as much.
So when I was in high school, the common was I don't like geometry. When I was in high school, I did the geometry part of the math competition every time for our high school team because people hated to do geometry and they wanted to forget the material as fast as possible. It was actually the class that made me a mathematician, or at least started me on the path, because I hate being told things. Well, it's because I said so. And I liked how clean geometry was. That doesn't necessarily mean I loved all the proofs, but I at least liked the intellectual honesty. In my chemistry class, you do all the following mixing, and if it's silver at the end, you have this, and if it's red, you have that. And I'm sorry you don't know advanced orbital quantum bonding theory, so I can't tell you why that's true. I didn't find that as satisfying. For the geometry, you could get to the stuff quickly. For a lot of math classes, you can get to the stuff quickly. For some of the more advanced stuff, yes, it does become almost, well, you don't know complex analysis, I'm sorry. But I can try to justify a little bit. What I really want you to get in the habit of is whenever you see something, try to push it further. And so many people don't do this. This is where the low-hanging fruit is. It's somebody's already done a lot of work and they've developed a theory. What else can you apply this to? Now that this exists, what can we use it on? All right, so here is a picture of a triangle on a sphere. And it's a right triangle. Now, in a plane, the sum of the angles of a triangle is always 180. What's the maximum you could have on a sphere? You could come all the way down to the equator, go a quarter of the way around the equator, and that'll be 90 degrees, and then come all the way back up to the North Pole. You can actually get 270 degrees on a sphere. The sum of the angles on a sphere is not constant. So the question is, what does the Pythagorean theorem look like on a sphere? Are there any special cases you want to look at? Or any special cases on the sphere where you know? Yes?
I think that big one you just talked about makes sense.
So in that big one, that might actually be an equilateral right triangle.
But indeed. So,
Things are strange.
yeah.
What kind of triangles might you have an understanding of on a sphere? So think back to what we did on the plane. We looked at infinitesimally thin triangles. Are there any kind of triangles you might have a sense of what it should be like on a sphere?
So, if you make the triangle like infinitesimally small, does it become like on flat?
Yeah, so if the triangle is infinitesimally small, it looks like you're on the plane. So there's a great article, I will try to remember to send it to you, by one of my favorite writers, Isaac Asimov, called The Relativity of Wrong, where he really goes off on people who believe that, well, everybody's wrong, so nobody's right. He goes, no, there's degrees of wrongness, and those of you who feel this way, you are actually towards the extreme of wrongness. And just, people used to think the Earth was a plane. And then they found it was a sphere, and then an oblate spheroid, as we started adding more stuff with general relativity, and the Earth, being bulged slightly at the equators. And if you want to say that people who said the Earth was spherical are as wrong as the people who said it was a plane, you're even more wrong than all of these people. Over very small portions, if it's a tremendously large sphere, it will look flat. And then whatever formula you have for Pythagoras on a sphere should reduce to Pythagoras on a plane. So we have some idea. So I'm going to write down spherical coordinates. There is a huge dispute as to how you should do spherical coordinates, depending on whether or not you are a mathematician or a physicist. I was trained by a physics department. I learned coordinates first in the physics department. So for me, my natural tendency is to have theta coming down from the z-axis and phi in the xy plane. So this is more the physics notation. Okay? And you could, of course, generalize this to higher dimensions. So I come down theta radians from the North Pole, and then I sweep around phi. Right? I'm not going to go through all the algebra in great detail. The slides have it all, so if you want to see it, you can go through it carefully. I just want to give you the sense of how you would attack a problem like this. So what would the Pythagorean formula be on a sphere? What should be involved in it? What quantities? Some quantities are obvious. What should come into play? Sniff out the formula. There's three that you should be able to give me without too much trouble.
X,
X, Y, Z, A, B, C, whatever we're calling the three sides. Those should definitely come into play for the formula. There's one other thing that should obviously come into play. Or maybe not obviously, but at least should be a candidate.
R.
Yeah, the radius. The radius of the sphere. So, and then if A, B, and C are small relative to the radius, it should reduce to planar. We can't have an equilateral right triangle with A equals B equals C as we mentioned. And it should only depend on the ratios A over R, B over R, C over R. So this is a really nice symmetric argument. And the reason is, if I rescale everything by a factor of 5, I don't really change anything relatively. It's like passing from one unit to another. And if I measure things in kilometers or miles or furlongs, doesn't matter. So whatever my answers are should only depend on those. So maybe a relationship involving cosines, as arc length is related to an angle. And so we've seen this before. Taylor expansion of cosine of u is 1 minus u squared over 2 factorial plus da 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 da. And if u is small, it's about 1 minus u squared. So let's calculate the cosine of a, b, and c over r. And we get 1 minus 1/2 a squared over r squared, and similarly for the others. And now, if we just notice the following algebra, if we multiply the two bases and expand everything out, well, you're going to get a 1 which will cancel from everything. The negative 1/2s cancel. And you get c squared is a squared plus b squared minus 2a squared b squared over r squared. Well, as r goes to infinity, if you fix a and b, they become the infinitesimal triangle. And this will reduce to Pythagoras. So this is not a proof that this is spherical Pythagoras, but it's at least a candidate. So I'm not going to go through the proof in detail. I will just go through the slides with a few seconds, so you can always hit pause. I will also post a link to the slides. We need the dot product of two vectors, which gives us the cosine of the angle between them. This is another reason why we like cosines of angles. Cosines of angles are related to dot products. Geometrically, this is what's going on. Right? And so then we use the law of cosines, which now we can prove because we know regular Pythagoras. So now we will do that. And now you can see why that was a homework problem that I needed you guys to do. And now we just go through, we put things out, we do some algebra, and after some algebra, we get the dot product is the length of v, length of w, cosine of the angle between them. This is a proof of the dot product formula. Now we take our points without loss of generality. You might as well assume your first point is on the North Pole. Then we've got our second points. We calculate the lengths. We use the dot product formula. We use Cartesian coordinates for the dot product. We have a right triangle. So we're going to adjust things a little bit in terms of where we choose our angles. We might as well make phi of a be 0, just rotate the sphere a little bit. Whenever possible, make your coordinates as nice as you can for the problem under consideration. Reduce the number of things going on. And so here are now my vectors that I need to look at. I have my dot product. I get the cosine of the angle as the following, substituting and doing all the algebra, and at the end of the day, the spherical Pythagoras pops out. So if you are interested in this, by all means you can do this. All right. Well, let's go further. What's the next natural candidate to look at after our success on the sphere? A hypersphere. So that would be another question as to, well, what happened in a hyperbolic space? Now, in several dimensions, Pythagoras is really still the same. If you have something in 5 dimensions and you have a right triangle, you can put that right triangle in a plane, so you can slice through. So the hypersphere, while a good thing to look at, might actually be the same thing. But it's a good thing to try. You're on the right track.
Cylinder.
So one thing is you could try a cylinder. So this is how you need to know a little bit more about other spaces. So anybody who's done some topology or some other spaces?
A mug.
So no, mugs are for coffee. No. It's getting a little hot. So I'm going to just write down hyperbolic. You could look at something called hyperbolic space. We've actually mentioned hyperbolic once in this class already. Anybody want to guess what the formula should be for hyperbolic space? We know the formula in spherical. Cosine is equal to cosine cosine. Anybody want to guess the formula in hyperbolic space? We have seen the functions.
With like cosh and
Yes! Basically search and replace. Replace all cosines with hyperbolic cosines because we're working in hyperbolic space. And you guess the hyperbolic cosine of C is the hyperbolic cosine of A, hyperbolic cosine of B, where the cosine is 1/2 e to the ix, e to the minus ix, hyperbolic cosine is 1/2. And so you have a lot of fun identities as you did with trig. Now it's actually the difference of the squares that's 1 rather than the sum of the squares. The angle addition formulas are a little bit nicer. You don't have to worry about which one has the minus sign. Neither does. Well, that's because this one now has the minus sign. So the minus sign goes to that. It turns out that is the correct generalization. And there is a Pythagorean formula in hyperbolic space, and there's at least a natural guess to try. All right, so conclusions. So there's a lot more that you can do. When you read a paper, when you're reading a theorem in a book, when you're seeing a research article, ask, what can I do next? What can I do from this? It's often the case that people have not pushed things as far as possible. The next one is different proofs highlight different aspects. I hope the dimensional analysis gave you a much better appreciation of why the Pythagorean formula is true, rather than I just did some calculations, and then it just popped out after the calculations. My proof of Morley's theorem is the worst proof of Morley's theorem. Right? I am an editor at some journals. I'm not going to abuse my power and get this published and put in print. It should not be in print. It's a terrible proof. It gives you the solution, but it gives you no understanding of why it is true. And then the last is trying to get a sense of what to try and what might work. Finding the auxiliary line. Finding the extreme cases to look at. That's what you want to do. It's not easy to do. The more experience you have, the easier it is to get a sense of that's a good auxiliary line to try. And then if it doesn't work, well, I'll try another one. Or what's an extreme case to look at? Let me send something to 0 or something to infinity, or make things symmetric. These extreme cases, that's how we build our intuition. All right, we've got 5 minutes left, so I just put some sabermetric stuff. So I'm not going to go through all of it. I'll just go through one thing. So assume Team A wins P% of their games and Team B wins Q% of their games. Here are 4 formulas to predict the probability that Team A beats Team B. One of these formulas actually does a pretty good job. 3 of the formulas suck. Which formula do you think does a good job? And what would you do to try to figure out which one? So I want the probability that A beats B. What can you think to try? Yes?
P is 1, Q is 0.
Yeah, so when P is 1, this is the team that always wins playing the team that always loses. Okay? You should beat the team that always loses if you always win. So if P equals 1 and Q equals 0, do all of these work? So this would be 1
They all work.
over 1. This would be 1 over 1. This would be 1 over 1. And this would also be 1 over 1. So they all work. They all pass that test. Yes?
They're 1 and 1.
I'm sorry? Okay, so now if you have 2 teams that always win, or 2 teams that always lose, you might expect that the formula should have trouble. Or what answer would you want it to give? A half. So it should either be a half or undefined. Years ago, my brother and one of his friends wrote a set of players for an old baseball game. They had the batter who always hit a home run every at-bat, and the pitcher who always struck people out. And they faced each other. And the old Macintosh just hung for a significant amount of time trying to figure out what to do. And then eventually, I don't know how the computer arrived at this, but it arrived after a significant amount of time with the only possible result.
Shutdown?
No. Double. It said, well, he always gets 4 bases. This pitcher always gives up 0 bases. Split the difference. We'll give him 2 bases. We'll give him a double. So you could try if they're both 1 or if they're both 0, maybe it should either return gobbledygook or maybe you should get a half. Another one is, what if both teams are a half? What should your probability of winning be? A half. So you could check and see, well, what happens if both are a half? What happens if my winning percentage, if team A is above 50%, and they play a team whose winning percentage is 50%? What can you say?
It's going to be above 50%.
It should be above 50%. More than that, it should be above whatever your winning percentage is. It should be above your P. Right? Because you say my winning percentage is P against average teams. Okay, no, so if you're 50%, then you're an average team. It should be exactly P maybe. And then maybe if you're below 50%, mine should be a little bit above my Q. So you could try looking at a bunch of these. You can try looking at special cases. Well, yeah, you really don't want to watch, the two teams that can't win play each other. Have I told you about the Georgia Tech Cumberland game? At some point we will talk about Georgia Tech Cumberland in football. The final score was 222-0. At one point, one of the Cumberland players was sick and tired of playing and decided to run away and hide. The problem is he ran to where other Cumberland players were hiding, and they said, "We don't want you bringing attention to us, get back!" So, but then this is a good one. If P is greater than Q, then what happens? And so when you start looking at it, eventually you see that you can rewrite things in a good way. And if you rewrite things in a good way, the algebra becomes clear. This is P times 1 minus Q, P 1 minus Q plus 1 minus P times Q. And now if you look at it, assume A has a good game with probability P and B has a good game with probability Q. So here A has a good game, A has a bad game, B good game, bad game, good game, bad game. And now we'll say if they both have a bad game or they both have a good game, play again. Otherwise, we'll say A loses, B wins, and now it's like a relative probability. And so then you would get the formula at the end. So again, this is a really good formula to predict a lot of things in the real world, and you can sniff it out if you have some thought as to what it might look like by looking at some special cases. So when you have complicated formulas, test and see, do you think it's true? All right.